Hi, my name is Sanjay Pathi. I lead AWS research in the worldwide public sector for Amazon Web Services. Thank you so much for joining today for the session on enabling researchers to work remotely using AWS. This session is really intended as an introduction to what AWS has to offer for researchers to help during this crisis to explore and optimize their workflows. We're going to talk about the impact of current environment and how AWS can help. We will also discuss AWS programs and awards that are relevant for researchers and talk about how we can get started with workshop and various educational opportunities. We are aware that many people are currently dealing with changes in their work, school, and community environment. AWS is taking measures to support our customers, our communities, and the employees to help them adjust to and deal with the situation. Working from home has become the new normal, so leveraging a public cloud is extremely important to perform research activities from remote environment. Fortunately, AWS has broad and deep capabilities that are essential and easy to implement. These capabilities include virtual research environment, serverless containers, as well as high-performance computing, research desktop, analytical services, machine learning. We'll talk a little bit about these things. Let's start with virtual research environment. Here is a classic example. I love it. Geospatial Center, funded by the National Science Foundation and NASA, just started using Amazon Upstream for the research workshop. They're using the LS Harris and Esri software and delivering at a scale. For 2020, they plan to support more than 300 students via remote learning method. This is a classic case where one can perform their research workshop from a distant learning mode. So we talked about Upstream. Upstream works with any open browser. It can be useful for university research, IT environment. One can manage it by the console. It's extremely easy to use, or with AWS SDK. There's no hardware or software needed to deploy. One can automatically scale on demand. It also provides some monitoring support. There are many other researchers, they like to have their own virtual desktop, and we have that. We call it managed cloud desktop for researchers. One can securely access a persistent desktop with a given CPU, memory, and storage. It works for Windows, Mac OS, or any iPad or any tablet. One can use it. More advanced researchers sometimes prefer a catalog of services. Here is an example where a catalog allows organizations to create and manage and govern various IT services. One can use EC2 or RStudio or Elastic MapReduce. Here is a GitHub link that one can use to get the reference architecture, and one can execute it itself. Service catalog sometimes is also useful to run a fleet of services, and this is really important for IT administrators. So one can run fleet of services on Workspace or AppStream or Connect, and these fleet capacities helps you to push the updates or delete using a bulk method, or push using a given set of CloudFormation template. Coming back to how researchers are using different components of underlying service, here is one example. The compute has structure is currently used in many ways. Various research organizations use what we call virtual servers or EC2. But there are many other organizations that use something like container management or container methods. So we have both Elastic Container Services as well as Kubernetes services in order for researchers to use it. Some of the folks use what we call AWS Lambda. It's really runs a code without thinking about server. So one can try out any combination, and it's really important to figure it out which workload is important for to run as a serverless mode, or can we use VM or given container methods. Here is a way of orchestration of those services. So AWS Parallel Cluster is built on popular CFN cluster, makes it easy to manage high-performance computing cluster on AWS. One can have their own supercomputer on AWS itself. NiceDB is a graphic-optimized streaming protocol that is well-suited for a wide range of usage scenario, ranging from streaming applications on mobile devices to HPC simulation and visualization. It lets you securely deliver remote desktop and application streaming from any cloud or any data center to any device. Here is another study recently we did where we did elastically expand a given cluster using GPU itself to perform a given study. So IceCube is an experiment which detects neutrinos from the sky. And this is needed in order to understand the structure of the universe. So in order to do that, they need a huge set of graphic processing unit or GPUs. That was not available at a given cloud or a given infrastructure. So they use HD Condor to elastically expand the infrastructure and ran more than 22,000 GPUs across the world, and in really elastic system. The same kind of principle of elasticity people use from Clemson, they were trying to study natural language processing. In order to study natural language processing, they need huge set of resources which was beyond the capability of their computing center. So what they did is they modified the provisioning system, or what people call scheduler, that automatically expands to AWS, provides a similar environment, and shrinks back. In this process, they created one of the largest cluster during that time of HPC cluster, just using spot instances and using one particular region of AWS. So they're on more than 1.1 million CPUs just in few hours. Imagine one need to procure 1.1 million CPUs. It's going to take a long time. So elasticity is really important when we do massive workloads and want to get it done very quickly. Another pattern I have seen is using more advanced technologies. So Children's Hospital Philadelphia and Edgar Genome, they were trying to study the genomics analysis of, for example, 1,000 genomes. So in order to do these kind of genomic analysis, it takes a large set of computer cluster for running for a long period of time. So instead what they did is they tried to use a little bit more advanced what we call FPGAs or resource hardware infrastructure, Amazon F1. So these FPGAs has one of the fastest accelerated cores within the system. So with using Amazon F1 instance, they could run 1,000 diverse pediatric genomes within 2 hours and 25 minutes. They got Guinness Book of World Record for fastest analysis for human genome. Another pattern I've seen for researchers, data sets are vital. And for research, one like to share their data sets on, and AWS allows that. So on AWS, anyone can analyze and build services on top of the existing infrastructure and can share the data sets. We also provide a registry of open data set on AWS to help people discover and share data sets that are available via AWS resources. Within the data sets, there are the three ways to do it. So one is what we call Open Data Program. Open data on AWS is how one can share any volume of data with many people you want. One of the popular interface we have seen is Globus for Amazon S3 that provides an instant link from Amazon S3, which is a storage element of AWS, to all other storage locations. Simply one would need to log in and seamlessly move and share data sets in S3 across any storage resources using a unified and very intuitive interface. Globus allows researchers to currently is being used more than 120,000 users across 600 identity providers. There's a third way of doing that is what we call AWS Data Exchange. It makes it easier to find and subscribe to using third-party data in the cloud. So for example, if you really have a set of data sets and you want to share only with 10 of your friends, not everyone in the world, AWS Data Exchange is an extremely nice tool which allows subscription-based mechanism for the resource provider or the data owners to share. In AWS, once we have the data sets, then I have seen many communities, they start building what we call data lakes. And data lakes are vital for analytics. And it's really simplest to build data lakes for analytics on AWS. We provide a huge set of services. it's also more secure infrastructure for analysis. We have most comprehensive and it's really very scalable at a cost-effective rate. So let me dive deep into this. So the way it starts is we start with data movement and a given set of migration of Amazon S3. Once you have the migration, you use the infrastructure and the security area to start building what is needed on top of the lakes for analysis, like data warehouse, big data processing, serverless computing. And once we have that layer done, then I have seen many of the customers or users, they use dashboard to see the results of the analytics, or use predictive analytics. We have a whole set of deep integration between all of the layer of analytics data that gives builders or users the tool to quickly analyze data using any approach. One can use AWS Lake Formation to store any data once in a given standard format in Amazon S3, and then analyze using the right tool for the job. For example, Hadoop or Apache Spark or data. And once you have a given analysis, then there are various ways to either one can do machine learning on top of that, or one can use QuickStart for visualization. So there's a huge breadth and depth of the services we have in order to do the right job. Here is an example I like. This is an open data lake which was created for COVID-19, and the statistics displayed is on for June 16th. And it's really extremely easy once you know the data source or data owner. And here is a blog which one can copy and paste and use it to build their own data lake with a given visualization. The same thing is true. One can use several analysis tools which is available for data lakes on AWS, how to do the lake formation. Athena is a serverless interactive query service one can use to build catalog. Elastic MapReduce allows to easily run Spark or Hadoop or Hive or Presto or HBase for big data related analysis. And then we have something called Kinesis, is a simple way for researchers to collect and process and analyze video and live data stream in real time. So we talked a little bit about machine learning. What I have seen with several of the users or researchers, typically machine learning is divided into three different categories. One is called supervised learning, another is unsupervised, and third is reinforcement learning. Most of the studies are either these three categories or a combination of two. In supervised learning, it's really task-driven. You have a training set of data set which has their feature and a given level. And what we're trying to do is predict, like the red dots here, predict Y. And the goal is to minimize some kind of a loss function. Typically, it's used for classification or regression. Unsupervised learning, on the other hand, is data-driven. You're learning for the feature from the data itself. So the training data sets consist of a given feature, and then one try to study how to categorize that feature or create a cluster out of it such that you can do a given set of classification. So in this, K-mean clustering is a classic example of unsupervised learning. The third sort we have seen is machine learning for decision making. For example, you have an X set of training data set which has a state and an action and a reward. So what you're trying to do is to minimize the action such that you can maximize the reward. So it starts with the agent which performs the action in a given environment, which gets a state, and if the entire process is minimized, then the person gets a reward. It's really used for robotics and games and various other applications. So while talking about machine learning, just to mention, we have a whole set of stacks for the machine learning. It really starts with machine learning at the framework or services at the infrastructure layer. It's really flexible in choice and it's high performance for the infrastructure. And then we have a little bit called ML services. This is needed to train and build machine learning model. And then we have something called AI services. This is simply to add intelligence to the application and for users who do not need to have machine learning skill. And it can be categorized in computer vision, for documents, for speech, for languages, chatbot, forecasting, and recommendation system. So if you look at carefully, we think about that at a macro level as having 3 layers. And in these layers, the bottom layer is the interface, which is for hardcore developers and who want to work with algorithms. At this framework layer, we support TensorFlow or MXNet, PyTorch, almost all popular algorithms. For example, TensorFlow has the most resonant and largest community today, and we have a lot of TensorFlow usage and experience. About 85% of the TensorFlow is running on the cloud, is running on AWS. So if you look at the second layer of the stack, which is the ML services, this is really for developers who wants to build their own model based on the lower frameworks like TensorFlow or PyTorch, such that they can iterate over to get the best possible hyperparameters or using a given loss function. On the top layer, we serve developers and companies who want to add solution-oriented intelligence to their application to an API call. Computer vision is a classic example for studying convolutional neural net that tells me, for example, what is there in this image, or which celebrity is in the image. Is this image safe for work? The same thing we do for speech, like Polly and Transcribe. If you want to turn text into speech, we have Polly, and if you want to transcribe audio, we have a mechanism called Transcribe. Here is a study done by the Stanford University researchers try to understand the complication due to diabetes. Users or people having diabetes can affect the nerve vessels in the eyes. So one of the way to do is to train using a computer vision a normal set of eyes, and any deviation in this nerve vessel, one can say that it affected the eye. The same thing one can do in this particular study is the skin cancer detection at a physician level or better, as all using computer vision. Here is another interesting study which came from UC San Diego Health System. Healthcare providers are now using various AI-related methods we talked about in a clinical research aimed to speed up the detection of pneumonia. Pneumonia is a condition which is associated with severe COVID-19. For most patients with COVID-19, the ultimate cause of the death was found to be pneumonia, a condition in which there is the inflammation and fluid buildup make it difficult for patients to breathe. So UC San Diego, what they did is their radiologists and various physicians, they got together and they started using some of these AI and machine learning technique we talked about, especially in the computer vision areas, to augment lung imaging analysis in a clinical setting. And they're using AWS, and this study was done using more than 2,000 records. I've also seen researchers use more of a studio environment where they start writing a code, start building it, and start training it, but wants to see the performance at the same time. So we developed something called Amazon SageMaker Studio that allows that one can, it's like you're writing the code and you're compiling it or you're training it to get your best optimal parameters or hyperparameters, but you can also see the performance at the same time. And many of the researchers are using Studio for that. So let's change a gear a little bit, and I'd like to talk a little bit about remote device monitoring. This is really essential for many of the scientists who want to monitor their labs or the lab devices from remotely. Because IoT solutions can be complex and can be multidimensional, we remove the complexity of implementing IoT. We help our customers securely connect to any number of devices to the cloud, providing the infrastructure to scale as needed as one gain insight into the IoT data. Customers are using AWS IoT at a massive scale across multiple industries, for industrial processing, to remotely monitor patient health, wellness, building a smarter product, grow healthier crops, transform transportation, and collect data at any scale. Here is what we have seen in a given architecture. It really starts with device software. Then one need to work on connectivity and control services, followed by analytics. We have IoT analysis services that can use to make sense of the IoT data at the analytic level. But the connectivity and the control enables you to control and manage and secure device at any given scale. The device software allows you to create the custom software to run your device at the edge. So it generally comes as what people call IoT vicious cycle, starts with the device software, goes to the connectivity and control services, followed by the analytic layer. One can start the device software layer using AWS IoT or SDK. We also have AIoT Greengrass framework one can use, or device tester. There are core services which one can connect called IoT Core. IoT device management helps you to manage a device, as well as Defender for the security purposes. And then we have on top of that analytical services like IoT analytics or IoT events, or sometimes you can start building graphs based on connected devices. So IoTs have huge use case we have seen. For example, AWS IoT helps Bayer Crop Science manage the collection, processing, analysis of seed growing data. Pentair runs its Bayer membrane filtration system on AWS IoT. Petabanana is a platform that provides communities with a real-time crowdsourced flood information through its IoT water level sensors. They leverage solar power and power management to make the sensors suitable for long-term or wide deployment in Jakarta. They're doing deployment in Indonesia and various cities. We have several programs and awards for researchers to get started with analysis or machine learning. So one of the programs I really like is AWS Machine Learning Research Award. It is very similar to the funding profile or funding agency model, where researchers write a proposal in their favorite machine learning domains. They apply. If they get selected, they get funded with a set of cash as well as AWS credits. We recently also are working in collaboration with various HPC Center, White House, on HPC on AWS for COVID-19 research. We also opened up a $20 million AWS diagnostic development initiative, which researchers can use for research related to diagnostic of COVID-19. For any generic research, we have something called AWS Cloud Credit for Research program, where, like any funding agency, one write a proposal and it is reviewed by a review committee. If it's selected, AWS funds it by its credit program. We recently started collaborating with National Science Foundation under the model of Cloud Access model. So NSF Cloud Access model helps nationwide researchers to benefit from access to the massive cloud infrastructure. Researchers and educators can receive technical guidance and training within this program. It maximizes access to the cloud resources as well as funding for the researchers. This award was given as Cloud Bank to UCSD and a few other institutions. Please do apply and request for Cloud Bank as your mechanism to use cloud. We recently created, in collaboration with National Science Foundation, a mechanism for researchers to use quantum computing. So this program is just live. It enables quantum computing platform on cloud in collaboration with National Science Foundation. Here, researchers can develop quantum algorithm and realize the experimental realization. One can use quantum compiler and run time-dependent infrastructure. One can design fault-tolerant computing, benchmarking of a given infrastructure. One can use Amazon Braket services with 3 different architecture type, including superconducting qubit, as well as ion trap mechanisms. So please have a look and apply. And if there is something interesting for you, let us know. In the biomedical field, we recently started collaborating with National Institute of Health to link biomedical data for researchers. As we know, biomedical data is all distributed across various areas. So this is an attempt for a common researchers to start using data set across different domains associated with the field. Under the stripes, one get a given incentive, but also access to more than 20 petabytes of biomedical data. And that is really vital to foster innovation in this particular field. We also provide workshop and educational opportunities like AWS Research Workshop on various topics. We provide Jupyter Notebook or hands-on experience on data lakes, AI and machine learning, IoT and genomics. We have security-related workshop. Please have a look here. We have container-based workshops on Kubernetes and HPC systems. There's a whole set of Amazon SageMaker workshop, which you can start using it via Jupyter Notebook. There is a really nice guide was written by a student on how to use AWS Parallel Cluster and Slurm and various scheduler mechanism for the climate science. We also provide various labs to get started with AWS on machine learning, data analytics, as well as various workflows. Here is one example of training pathway where we start with compute-related system and try to do hands-on experience on batch system and then containers. And so once you start building that with storage and data lakes, one start developing analytics and machine learning on top of that. So in conclusion, AWS offers services that enable the work of researcher remotely. It has the broadest and deepest selection of services. We provide grants and programs to support research and researchers. There are many resources and training that we offer to get you started. So please do have a look and get started. Thank you so much for coming. And please fill the session survey. Thank you so much.